Today we will do some examples concerning the dispersion models. Essentially what we will try to do is to develop the relationship between the sources and its impacts. You will recall that we had done the dispersion modeling, and in the dispersion modeling one of the most popular models that we learned, and we did some examples before, was using the Gaussian plume models. Gaussian models can be applied to a point source like a chimney. It can also be applied to a line source like number of vehicles which are moving on a highway and we want to see its impact. Gaussian model can also be applied to an area source, okay, with the group of small industries are there. So, we can also find out the impact of the emissions from such sources in the ambient air. So, this lecture today is completely devoted to the certain examples that we want to do. Okay, here is a question, and what I would do is that we will read the question very carefully and then we will solve this question right here in the class, and in the process you will see that I have a calculator here with me and I will be doing certain calculations with the help of the calculators, and we will try to write the numbers on the screen. Okay, so, let us read the question very carefully. The question is, an air sampling station is located at an azimuth, I will explain you what is the meaning of azimuth, of 203 degrees from a cement plant. At a distance of 1500 meter, the cement plant releases fine particulates, okay, the size of the diameter less than 15 micron diameter at the rate. So, the emission rate has been given to you as 94.5 grams per second from a 30 meter stack. Okay. The stack height is also given, and the question is, what is the contribution from the cement plant to the total suspended particulate concentration at the sampling station when the wind is from 30 degrees and the wind speed is 3 meters per second on a clear day in the late fall at 16 hours. Okay. So, we will try to do this problem, and you will see the Gaussian plume model will be using the Gaussian plume model, and for the convenience I have given the formula already for the Gaussian plume model on the screen, as you can see. You would also recall that, well, Q is the emission rate, okay, and Y is the cross wind direction, H is the effective stack height, sigma z is the dispersion parameter in the z direction, okay, sigma y is the dispersion parameter in the y direction, as you can see here, u is the wind speed, okay, and c is the concentration which is at distance x, crosswind distance y, ground level, because z is 0 here you can say, and emission is from height h. Before, we like to use this formula that we had already derived in our earlier classes, but first of all, before we even touch the formula, let us understand what the question is. Okay. So, question is telling us that there is a source. So, let us draw a source. Suppose this is the cement plant, that has a chimney here, and there is a station, okay, sampling station, where at an azimuth of 203 degrees. So, let us see where the station is. If you recall, how do we look at the azimuth? Suppose this is my north, south, east, west, and we, as you remember, when we were talking about the wind direction and all, we said the azimuth is 203 degrees, is that we measure the angle of 203 degrees from north, okay, and then we say, okay, this is my, so my station is located somewhere on this line, okay, and this angle is how much? 273, beg your pardon, it is 20 203 degrees. Okay. So, and my, as per the question it says, and where it is, how far it is located? The cement plant, okay, it is located at a distance of 1500 meter. So, if I go in this direction 1500 meters, okay, let us try to make it as straight as we can, and this is where my sampling station is there. So, this distance, okay, is 1500 meters. Okay. All right, this is the location of the sampling station. In addition, the question says that the wind direction, okay, let us forget about the emission of the timing. The wind is from 30 degrees at 3 meters per second. So, 30 degree is the wind direction. So, I have to go 30 degrees, okay, and show you the wind direction, and the wind is going like this. Okay. So, how much is this angle? So, I'll just, for the convenience, I'll remove this now. Okay. So, this is my wind direction. That's where the wind is blowing, and this is my cement plant. And here I have set up a sampling station. Here is my, I can even show you, this is my sampling station is located here, and wind is blowing in the direction as you see here. Okay. You can find out how much will be this angle. Okay, it does not take long. This angle will be 7 degrees. Okay, that you can see for yourself. The angle between the direction of azimuth at which the station is located and the wind direction is 7 degrees. Okay. So, let us even write it clearly so that there is no confusion. Seven degrees is this angle. Okay. Now, if you recall, okay, in the Gaussian plume model, okay, that is the model you see here. Always remember the direction of the wind is the direction x direction. So, this is my x direction. Okay, x direction. Okay. And so, I need to know the distance from here to the corresponding distance, that is the component of this station in this direction. Okay. So, I can draw a perpendicular, okay, from the station, and then I can find out the distance, this distance, because I need to know the distance in the x direction. Okay. So, I can find out this, and always remember the direction the direction which is perpendicular to the wind direction, which is this direction as you can see here, okay, is my y direction. So, if this was my x, this is my y direction. Okay. Let us make it a little better. Okay. So, now I can find out x equals to, because this is what, this was total distance from here to here, okay, from where, here to here, as I am moving my, was 1500. So, my x equals to taking the component of this distance to, or taking this component on x direction. So, my x will be 1500 cos 7. So, that comes out to be, if I use the calculator, agreed. Okay. Similarly, I can find out the y component, okay, and call this as y, and my y will be equal to 1500 sine 7 degrees, and that, if I do use the calculator, that came out to be 87 meters. Okay. So we have find out, see, if the wind direction and the direction at which the station was there, then we didn't have to find out the x and y direction. But since the station was little bit not along the line of wind direction, so we have to find out the x component and y component on the x direction and y component on the y direction. So we now understand the meaning of azimuth. Now we understand the meaning of wind direction. So now what I will do is, this picture which I have drawn for the clarity, I will rub this picture. Okay. And what is the objective? Let us say what we need to find out. We need to find out the concentration at x equals to 1489, y equals to 87, z equals to 0 from a chimney, which is my cement plant in this case, located at a height of 30 meters. So let us write 30 meters. That is what my objective is, that is what I need to find out. Okay. Once we know this, life is simple. What we need to do is to look at the other things in the formula here. That is the Gaussian plume model. So Q, I need to know the Q. Q is given to me as 94.5 grams per second. Okay. Very good. That information is available to you. Okay. Let us see. We also need, this is pi. Okay. So pi is known to us. We also need to know the U, that is my wind speed. What is the wind speed given? 3 meters per second. Fine. That is also known to me. Okay. Then where is the problem? We also need Y. Y is also known to me, that is 87 meters. Okay. Do I need the x? Well, I do not need the x in the formula, but I will be requiring x in some sense, and we will see it how. You also need to know the h. Okay. The h is given to me, let us read the question, from a 30 meter stack. So stack or the chimney height is 30 meters. So let us write h equals to 30 meters. Okay. What else we need? Okay, I think we almost have everything except sigma y and sigma z. That is not known to us. But if you recall, when we had developed the Gaussian model, okay, you will recall the sigma y and sigma z both are function of downwind distance x and stability, and stability was the indicator of what? Stability was the indicator of atmospheric turbulence. Okay. So we need to find out sigma y and sigma z, and for that what I need x, okay, which is equal to 1489, and but if you recall, sigma y sigma z is also function of stability. So I also need to know the stability. So with the knowledge of stability and the information given to us on a clear day, okay, and late fall, that is like something like October, November. So the time is 16 hours. So that stability will be somewhat unstable. So you will recall the stabilities were A, B, C, D, E and F. Okay. So here the C is the stability, which is, well, don't confuse this C versus this C. Let's write this then in that case, okay, C concentration or something, CC. But this is a stability class C. So C is my, here what I am taking is the stability class. and what I will do is now I will determine the value or find out the value of sigma y and sigma z as function of two things, x and stability class. So, stability is also known to me. Okay. So, I will go to the charts. You recall we had discussed about the charts, and then we will go and use the charts and try to find out what is the values of sigma y and sigma z. Sounds good. So, what I will do is that quickly I will go to sigma y sigma z graphs. Bear with, some of the things show up on the screen. Okay. If you recall that these were the graphs that we had discussed when we were talking about the model. So, this side, okay, this side is my sigma y and this side is my downwind distance x. You probably cannot see so well, but these units here are in kilometer. Okay. This is 0.1 kilometer and this is my 1 kilometer and this is my 10 kilometers. And what is my downwind distance? What is my x? 1489. Okay. So, for this 1489, and here on the you are seeing that class A, class B, class C and so on and so forth. What was my class? My class was C and my downwind distance 1489. So, let me start from 1489 and let me hit to C for that matter. Okay. So, for that matter let's start and with 1489 approximately. It won't be so easy for you to do it, but I will do this one for you, and let's go and hit to C. Okay. So, this is my C graph, and then I can read this value as I go on to. Okay. So, this is my, so may not be very clear to you, but this number, if I do exact this thing, that is coming out to be 150 meters. So, in a way I have been able to find out sigma y equals to 150 meters. So, let us do the same thing for sigma z. Okay. Okay. So, this should be standard deviation, it should be z direction. Okay. So, now again I go same distance 1500 1489. Okay. Stability class is also same. Okay. And then again let us try to find out what will be the value of sigma z. So, we go on this graph to find out the value of sigma z. Okay. You come here and then you move on to the y axis and you come here, and this is coming, I can write here 87 meters. So, my sigma z is 87 meters. See, so I could find out the value of sigma y and sigma z, because I will need to use again. So, well, let's okay. So, let's go back to the slide where we needed the value of sigma y and sigma z. So, if you recall, what was the value of sigma y that we got from the graph? That was 150 meters. So, let us write here, and sigma z, if you recall, how much was sigma z? That came out to be 87 meters. Okay. Now, I am more or less, I have everything that I need to know to be able to find out the value of concentration or impact of a cement plant on a sampling station. Okay. So, simply I can do the C or CC as I am trying to call it. Q is how much? 94.5. Okay. Pi is 3.14. U is 3 meters per second. Sigma y is 150. Sigma z is 87. Okay. And then the exponential term, I will write this underneath here, exponential of what? Minus 1 by 2. Y, what is the value of y? Y value was, y value of, no, we made a mistake somewhere. Okay. So, the mistake was this one. Okay. So, in fact, this was 183. So was this. So let's say, so 183 divided by the value of sigma y is 150 whole square bracket close times the value related to h by sigma z. So that is again exponential 1 by 2. What is the value of h? 30. What is the value of sigma z? 87. I will remove square and bracket close. Okay. So remember that the y was equals to 183 meters. So this, if you do run through this calculation, which you can, okay, and that thing comes out to be 3.4, as I did my calculation on the calculator. (3.4) into 10 to the power minus 4 grams per meter cube. Okay, is it clear or not? Let me make it amply clear for you. Okay, so this is the concentration that I estimated. So I have answered the question that asked me if there was a station which was located at the azimuth of 203 degrees from a cement plant at a distance of 1500 meter, and the wind direction and the direction in which the station existed was not coinciding. So I had to find out the angle between the direction of the location of the station to the direction of the wind. That came out to be 7 degrees. Then I found out the x component and the y component, okay, and this is 183, 1489, and then I write down whatever things available to me. Sigma y and sigma z I said was a function of the downwind distance x, that was 1489, and also the stability, and stability we estimated as class C, and we use the graphs to find out the value of sigma y and sigma z. Once the value of sigma y and sigma z was known to me, final concentration was calculated using the model in which everything was known to me. Okay. So if that is clear, we will go and do the next example. This example is a little well, I will not call it difficult, but it will require some understanding of the problem. Okay, the problem reads like this: a dispersion study is being made over a relatively open terrain with fluorescent particles. Okay, we are trying to do some measurement of the fluorescent particles whose size yields 1.8 into 10 to the power 10 particles per gram of tracer. Okay. See, well, let me also give you a little background. The tracer studies. What are the tracer studies? See here, what we do is, normally if we have a source, okay, suppose this is emitting SO2, and you want to see its impact somewhere here. How much is the contribution? Or for example, this is a refinery, and this is some important building, or well, let's say Taj Mahal, for example. It's just an example that I am giving you for the explanation. So what happens, I want to find the exclusive impact of SO2 from the refinery to Taj Mahal, but I cannot do it because there are many other small sources that also can contribute SO2 to Taj Mahal. So when I am doing the measurement is a mixture of SO2 that has come from many places, but here I want to find out only the contribution, let's say, from a refinery. So what I can do in refinery, along with SO2, I can put some tracer, okay, and that tracer will be emitted only by the refinery, because I am mixing the tracer, and there will be no contribution of the tracer that will be coming from any other source. So then if I am looking at the tracer now, there is no question of other sources contributing to the tracer, okay, and what I am measuring here is the tracer, and this tracer compound, whatever that may be, generally that compound is okay, or whatever that could be, like the studies on what tracer should be there, that also is interesting thing. But here we are trying to look at the what will be the impact of the tracer. So, that is the background of the tracer. So, let us take this one out. So, we are actually, what the question is about, actually we are planning a tracer study, and in that tracer study we are saying how much is the tracer quantity that we need to put in the system, okay, and that should be emitted out. So, we will read it again. A dispersion study is being made over relatively open terrain with fluorescent particles whose size yield 1.8 into 10 to the power 10 particles per gram of tracer. If I am using only 1 gram of tracer, how many particles that will be emitted? 1.8 into 10 to the power 10. Okay. Sampling is by membrane filter, through which 9 into 10 to the power minus 3 meter cube of air is drawn each minute. Okay. A study involves 1 hour release, okay, 1 hour release of what? 1 hour release of tracer, which can be considered from the ground level. Okay. If I am considering the ground level, it means my H is 0. Okay. Is to take place during the conditions forecast to be slightly unstable. You recall, if slightly unstable means the class is stability C. Okay. With a wind speed of 5 meters per second, it is desirable to obtain a particle count of at least 20. So, wherever I am doing the sampling, in order to get a good tracer amount on my filter paper, I must ensure at least 20 particles are captured at the sampling site. 20 particles upon membrane filter located at a ground level 2 km from the plume central line on the sampling are 8 km from the source. What should be the total release be in grams for this run or for this study? So, what we are trying to say here is there is a source where we are releasing the tracer, okay, and we are doing the measurement here. This distance is 8 kilometers and located ground at 2 kilometers from the plume central line. Then this is my plume and this is my 2 kilometers. Okay. All right. If that is the case, I have to find out the total quantity that I need to release. Okay. So, we will remove this for the time being and try to write the model once again. C was equal to Q quantity, or the emission rate was pi U sigma y sigma z, okay, exponential minus 1 by 2 y by sigma y square, and there will be no h term because h is equal to 0. Because why h equal to 0? Because the source is at the ground level. Okay. So, this is the formula that we need to use. Okay. Let us be a little bit careful about the units here. The C is in, let us say C, whatever units you want to take, okay, you want to take in something like grams per meter cube, and my Q is in grams per second, pi is unitless, U is meters per second, sigma y is meters, and sigma z is again meters. Okay, and then same, this is will be unitless thing. Okay, and you see, does it make sense dimensionally? Yes, it does. Okay. So, if I say the quantity that I am releasing, okay, is for the 60 minutes. So, here the I can see this, I can write this in place of Q, I can write here QT, okay, and then for like it was for 1 hour. All right. So, what I can do is I can take this unit seconds on this side, and I can write this as grams per meter cube second. So basically this Q, I can write this as Q2, which is exactly the mass that I need to emit, okay, and rest of the things can be simply the same. Okay. So I need to find out this quantity. Okay. All right. I need to hear grams. Okay. I need the unit grams per second per meter cube was my QT. So only the mass, that's a gram. Okay. U sigma y sigma z, and let's not forget about the pi, and exponential minus 1 by 2 y square upon sigma y square, or something like this. So this is what I need to find out. The condition given to me is that I need to capture 20 particles, okay, as per the questions. So what will be the mass of 20 particles? Okay. If you recall from the question, 1.8 to 10 to the power 10 particles are released when the mass is 1 gram. Let's do from the basic principle. So if the particle is 1, then mass is 1 by 1.8 into 10 to the power 10 grams, and I want to capture 20 particles. So how much is the mass that I'll capture on the filter paper? 1.8 into 10 to the power 10 times 20. So that is the mass that I want to capture on my filter paper. Okay. But here I want the units to be grams per second per meter cube. So this grams, okay, that is my 20, 1.8 to 10 to the power 10. If I divide this by the flow rate of my sampler, let's go back and we can see that what is the flow rate at the sampler. Okay, where is the flow rate? The filter through which 9 into 10 to the power minus a meter cube of air is drawn each minute. Okay, so let's go up and 9 into 10 to the power minus 3. So this is my 9 into 10 to the power minus 3. Okay, units will be my minutes per meter cube. Okay, this I can convert into seconds. For seconds I need to multiply by 60, and now finally overall the units I am getting is grams second per meter cube. And I did this calculation, and you can also check such a calculation as no, we made mistake again. We need to divide by the flow rate. So this should be 1 upon, what was the flow rate? 9 into 10 to the power minus 3, 9 into 10 to the power minus 3 meter cube per minute. So this will become minute per meter cube, and this will become 21.8 10 to the power 10 minutes. We can convert into the seconds. 9 into 10 to the power minus 3, and that will come out to be equal to, I can use the calculator here to find out the things, and this value comes out to be 7.41 to 10 to the power minus 6 grams second per meter cube. Okay, so now I can remove this. Okay, and then I can write here 7.41 10 to the power minus 6 grams second per meter cube. Qt is that I want to find out. What was my pi is 3.14. Wind was how much? You remember, wind was 5 meters per second, and I again need to find out sigma y and sigma z at what distance? At 8 kilometers. So I'll use the same the graphs. Okay, and I found out sigma y, that was equal to 690 meters at what distance? At 8 kilometers. At 8 kilometers. And sigma z, that again I'll use the graphs as we did last time. At what distance? At 8 kilometers. If you have any doubt, we can quickly check. 6 sigma y at 8 kilometers. Okay, so this is the distance. This is 10 kilometers. This is 9 8. So you go along the 8 kilometer and hit to C here, and then comes this direction. Okay, and you'll find this value here is 310 meters. Similarly for sigma z, 8 kilometers, 10 9 8. Hit to C, somewhere here, that value comes out to be this, actually I'm sorry, this came out to be 690 meters, and this also is meters. Okay, so we have sigma y as 690 and sigma z equals to 310 minus half. What was the value of y? 2 kilometers, so that is equal to 2000 meters divided by sigma y. Sigma was how much? 690, the whole thing square. Okay, solving for qt, okay, that came out to be grams. Okay, so this is what is the answer to the question is that we should put so much grams of the tracer in the process so that it will be emitted, and once we are capturing it at a distance of 8 kilometer downwind, 2 kilometer crosswind, we will be able to capture at least 20 particles of the tracer, which was the fluorescent particles. Okay, so that answers the question, but we can quickly take the recap of the whole thing. This is my standard Gaussian formula. I need to find out the quantity qt which I need to release. I can, in this step, what I did is I just put the units for the clarification, and then I said this is what is the total quantity that I need to know. So this second I sent on to this side, and this is the quantity I want to estimate first, and then I want to go on qt. So the next step what we did was we tried to estimate this quantity, and for this quantity we did the calculations which are here. Okay, for the 20 particles this will be the grams. Okay, so many grams for the 20 particles that I want to capture. This is the flow rate, and then this flow rate I converted this into the seconds here. Okay, and the final answer came out to be 7.41 10 to the minus 6 grams per second per meter cube. So I used this information here, and then I estimated for QT, and everything was known to me. The sigma y and sigma z I calculated using the graphs for the which were depending on the stability and the downwind distance, and downwind distance was 8 kilometer and the y is 2000 kilometers, because this station was located at the 2 kilometers or 2000 meters crosswind of the wind direction. This is how I can even find out the quantity of the tracer. Okay, we will do another example, again trying to estimate the impact of the emissions of vehicles, okay, onto a point of our interest. Okay, so let us read the question properly. An estimate is required of the total hydrocarbon concentration 300 meters downwind of an expressway at in the afternoon 15:30 hours on an overcast day with wind speed of 4 meter per second. Okay, so let us see, u is given to me, okay, as 4 meters per second. The express runs north south. Okay, the expressway is running north south. So this is, suppose this is my north south. Okay, the road is like this, and I have this many number of vehicles going on the road. Okay, and then it says express runs north south and the wind is from the west. So wind is from the west. So what we say, wind direction is like this, wind is from the west. Okay, what else it tells us? Express runs, okay, from the west. The major traffic flow is 800 vehicles per hour. Okay, the vehicle flow (8,000) vehicles per hour. Okay, and the average speed of the vehicle is 40 miles per hour. Well, we will change this 40 miles in the meter. Let us say, wait for a moment. Vehicle speed is 40 miles per hour. Okay, and it is also given that at this speed the average vehicle is expected to emit so much grams per second of the total hydrocarbons. Okay, fine. That is, each vehicle will emit so much. Okay, if you recall the formula that we used or that we developed for the expressway or for the line emissions was x, the concentration, c at any distance x, y equals to 0. Okay, why y equals to 0? Because where I want to find out the concentration is also coinciding with my wind direction, which is my x. So my y on this line is all 0. Okay, so y is 0. We want to find out the ground level concentration, that is 0, and my height of the emission is also 0. I can consider that to be the source being at the ground level. Okay, that if you remember, that was 2q root 2 pi, this formula we had derived earlier, sigma z u. So sigma z and you understand, but here the q is the emission rate okay, in what units? Grams per second per meter. Okay, fine. And what is information available to you? Available 2 grams per second. So I need to find out the emission in terms of the grams per second per meter. That's what is my requirement. So I have to be a little careful in finding out the. So what I'll try to do is, the first, that might be a good idea, to find number of vehicles per meter. That I can do very easily. Okay, vehicle flow okay, that will be number of vehicles per hour divided by the vehicle speed. Okay, let's say that speed I have in meters per hour. So what my final answer will be, number of vehicles per meter, and that's what I need to do. So let's try. So we go vehicles flow, that's number of vehicles per hour is 8,000. So let's write here 8,000. Okay, that is vehicles per hour. Okay, and the vehicle speed is how much? That unfortunately is in miles. So 40 miles per hour, but this I can convert into the meters. Approximately that will be equal to, if I multiply by 1600, okay, and this will be meters per hour. The final answer will be in the meters per hour. So I can remove this, okay, and this thing will comes out to be equal to, I have to do some calculation here, and that comes out to be I'll do the quick calculation here, because I'm using, essentially, as you are seeing, I'm using the calculator here. Okay, interesting. Vehicles per meter. Okay, so now we are all set, and we can use the information here, and C equals to, what is 2 times the Q, okay, that is 0.125 vehicles per minute, and each vehicle, how much each vehicle is emitting? 2 into 10 to the power 2 grams per second. So each vehicle, so I have only 0.125 vehicle, so I multiply this by 2 into 10 to the power minus 2. So this is what essentially I got the, this is my Q, okay, divided by 2 into 3.14 times sigma z. I need to find out the sigma z. Okay, what was my stability class? Okay, I need to know the stability. Did it say anywhere? Overcast condition. Overcast means, if you recall, we had explained to you, overcast condition means stability is equal to D. Okay, so let's take the stability. So we, and what is the distance from here to here? X distance. Okay, let's, oh, I forget, let's see what the distance is. Experience south wind from the west, the measured flow is concentration 300 meters. Okay, very good. So this is 300 meters. Okay, so I need to go to my graph, okay, and I'm only interested, this time I'm only interested in sigma z. Okay, so let's find out the sigma z, as we have been doing in past. Is sigma z is here, and the distance was only, this is 1 kilometer, my distance was only 300 meters. So this is 0.1, 0.2, 0.3. So this is my 2, 3. So I go here, keep going along this line till I hit the D. Okay, this is D. So I'm hitting this graph and go this way and find out, and this comes out to be 12. Okay, so we go back to our calculation site, and then we say okay, sigma z was 12. Okay, and what was the value of u, the wind speed? Wind speed 4 meters per second. So this is 4 meters per second. And now we have to simply do the calculation, and let's see if I do the calculation how much that is coming out to be. 2 times 0.125 times 2 exponential 2 is so much, and divided 2 times 3.14, we take the square root of that, multiplied by 12, multiplied by 4, this much, and well, it comes out to be 4.15. C equals to 4.156 into 10 to the power minus 5 grams per meter cube. That is the impact of the highway. So this also I can say approximately 41.5 micrograms per meter cube. So this is what is my final answer. So that is the impact of the vehicles onto the 300 meters in the perpendicular direction of the flow of the vehicles. So that's the final answer. See, this way we can utilize the models to find out the impact of any source. It can be chimney, it can be power plant, or it can be vehicles.